Covalent bonding implies the sharing of electrons between atoms, but just like with children, not all sharing happens equally. So consider the following three bonds. Each of these three situations can be considered a bond. In the case of the H2 molecule, you have a covalent bond. In the case of the carbon to chlorine bond, that's also covalent. And the NaCl bond is an ionic bond. And you may have noticed that the placement of the electrons that constitute the bond is different for each of these three situations. In the case of the H2 molecule, the two electrons are located exactly in the center of the two nuclei. You have a perfectly equal sharing of bonds. And this equal sharing of bonds is known as a nonpolar situation. The middle example, the carbon to chlorine bond, the electrons are much closer to the chlorine than they are to the carbon. This is an unequal sharing of electrons. The chlorine is taking more of the electrons effectively, and this is a polar covalent bond. In the case of the sodium chloride bond, the sharing isn't even unequal anymore. It's stopped being sharing altogether. The chlorine atom has stolen the electron from sodium in order to become the chloride ion. It's a complete, more or less, transfer of electrons. And that makes it ionic rather than covalent. And these differences in how the atoms are sharing their electrons or stealing them outright in the case of the ionic bond is due to differences in the electronegativity between the different atoms involved in the bond. So, in the case of the H2 molecule, hydrogen is the only atom involved in the system. Each hydrogen atom is going to have the same electronegativity because it's the same atom. And that means that each hydrogen is pulling equally strongly on those electrons, and you end up with a completely nonpolar system. In the case of the carbon and the chlorine, chlorine is far more electronegative, and carbon's electronegativity is much smaller. And that means that the electrons are going to preferentially go towards the chlorine and away from the carbon. And that means that the electron density in that system is shifted a little bit, and it's slightly negative on chlorine's side and slightly positive on carbon's. And in the situation of sodium and chlorine, chlorine's electronegativity is much, much greater than sodium's. You may remember from when we learned about electronegativities that it's possible to quantify the electronegativities of different atoms. And you can use the differences in electronegativities between the atoms involved in a bond to determine whether or not a bond is polar. And we'll do that for three examples. And here I've switched the second and third examples to involve fluorine rather than chlorine, just to make the results a little bit more extreme so we can show representative situations. When we talked about electronegativities earlier, I mentioned that we can quantify those numerically using a bunch of different systems. This example on the table shows a periodic table with Pauling electronegativity values, but whatever table you find or whatever table is in your textbook is certainly good enough. So we'll look at the electronegativities between hydrogen and hydrogen, between carbon and fluorine, and between sodium and fluorine. And for the sake of visibility, I'll use a slightly different version of this chart. Hydrogen's electronegativity is 2.2. So the difference between hydrogen and hydrogen is 2.2 minus 2.2. So there's a 0 difference in electronegativity between hydrogen and hydrogen, implying that the electrons are going to be shared evenly between those two atoms. And if we look at carbon and fluorine, the difference is between fluorine's 4.0 and carbon's 2.6. And that's a difference of 1.4. And if we look at sodium and fluorine, the difference is between 4.0 and 0.9. And you can see that there's a range of values for the electronegativity difference that run from 0 to upwards of 3. And at the low end, 0, you have completely nonpolar situations, and upwards of 3, you have totally ionic situations. And for the carbon-fluorine bond in the middle, you have an electronegativity difference somewhere in the middle, in this case around 1.4. This trend from nonpolar covalent all the way to ionic exists on a bit of a spectrum, and looking at it strictly numerically leaves out a lot of nuance. But a rough guideline is that any bond with an electronegativity difference of more than 2 is generally considered ionic. Anything with an electronegativity difference less than 0.5 is effectively nonpolar. And anything in between those two values, 0.5 to 2, is some sort of polar covalent bond. And we can represent the unequal sharing of electrons in polar situations using the concept of partial charges. So if we look at the hydrogen fluoride molecule, HF, hydrofluoric acid, we have hydrogen, which has a fairly low electronegativity, and we have fluorine, which is the most electronegative element in the periodic table. So right away we know that there's going to be a difference between the electronegativity values. We don't know yet where this will fall in the range between nonpolar and ionic, but we do know that there will be an electronegativity difference. And we know that fluorine is more electronegative and hydrogen is less, so we know that the electrons will be closer to the fluorine. And that means the hydrogen side of the system is going to be slightly positive, and the fluorine side of the system is going to be slightly negative. And we can write this a different way. We can use a lowercase delta. So a delta positive or a delta negative, representing a partial positive or partial negative charge. And because the electrons are shared unequally, the fluorine will be slightly negative by a certain amount, and the hydrogen will be slightly positive by that same amount. And there's one additional way that we can represent these distributions of charges, and that's using a dipole moment vector. And in the case of the HF molecule, it's drawn like this, where you have a plus sign on the side that's positive and an arrowhead on the side that's negative. And dipoles are simply a charge separation. So a slight amount negative on the fluorine side and a slightly positive by the same amount charge on the hydrogen side would represent a dipole. So a negative pole and a positive pole. And you can use this kind of system for working out whether or not any bond between any two atoms is polar. And a quick kind of rule of thumb is if it's the same element involved in the bond, so hydrogen to hydrogen or carbon to carbon, then the electronegativities will be the same and it's got to be nonpolar. But if the elements are different, the electronegativities are almost certainly at least a little bit different, and the bond will be slightly to enormously polar. The polarity of bonds is important when we're talking about things like properties of molecules or reactivity of molecules. So remember that positives and negatives attract. So polar bonds are going to be attracted to other polar bonds or to ions. So think about the situation you have in the water molecule. The oxygen atom is more electronegative than hydrogen, so each of these bonds is going to be polar. Each bond is going to be slightly positive on the hydrogen side and slightly negative on the oxygen side. And what this means is the oxygen side of this molecule, if you draw a plane in between the oxygen and hydrogen molecules, the oxygen side of this molecule is going to be slightly negative, and the hydrogen side is going to be slightly positive. And that means the oxygen in a water molecule is going to be attracted to positively charged things, and the hydrogens are going to be attracted to negatively charged things. This can involve attraction to ions, or it can involve attractions to other polar molecules. So you never have one water molecule floating on its own. There's always going to be lots of other molecules associated with it. And that means that the molecules are going to line up. Another water molecule with its slightly positive hydrogen atoms is going to associate with the slightly negative part, the oxygen, of another water molecule. And this can happen on a large scale with lots of water molecules associating with one another. And you end up with an attraction between these molecules. Remembering that positives and negatives attract, the slightly negative oxygens and slightly positive hydrogens are actually going to attract one another a little bit. It won't be as strong as a regular covalent or ionic bond, but there will be a little bit of attractive forces pulling these molecules together. And this has all sorts of implications for the properties of water. And kind of by extension, any polar molecule is going to have interactions with itself and with other molecules. So there are implications for the properties of almost all molecules.